live. I'm Katleho and this is Tracy.
Hello, Katleho. That was good. Wow.
Yeah,
We're so excited. My goodness. Well, we're here.
How are you?
Fine, and you?
Good, thank you.
It's Tuesday already. Can you believe it?
It is. I can't believe it.
I know.
When did Monday go? When was Monday?
I don't know. I lose track these days.
I know.
Yeah.
Anyway, what are we doing today?
Today, we're going to do graphs and equations of motion.
Okay.
So last week, Phil very nicely did some graphs and did instantaneous velocity and average and all sorts of things. So we're going to do a little bit more graphs today, and then we're going to jump into the thing the great teens really love.
I know.
Or not.
I know.
Equations of motion. So it's actually a really nice section. It's
Okay.
lots of calculations, no experiments, unfortunately. But
Okay, but that's okay.
it's all calculation based, but it's really
So
cool
they're going to
stuff.
be taking notes.
Yes, and they're going to get the calculators out, and they're going to make sure they know what we're doing.
Okay,
Yeah.
cool.
Cool.
You can go prepare that, all
thank
that.
you.
While
Okay.
I let you guys know about our prizes. Because it's Tuesday, guys, you know that we have plenty of prizes. We have our Casio labeler, and we have our Casio calculator. And by now, you know, grade 10s, that this goes out to the most excitable mindsetter on the page. Facebook.com/learnextra, and our Twitter handle is @learnextra. Guys, you can ask anything that you need to ask. This is good because I know that some of you have done this in class, so this is nice to revise it. And if it's the first time you see it, get that paper and pen out and start jotting down notes because you are going to be ahead of the rest. Thank you to Liberty for bringing us such an awesome show. Over to you, Tracy.
Oh, thanks, Kakleho. Okay, brilliant. Guys, get going on the Facebook page. I have one of those labeler thingies, and it's my favorite toy. Anyway, moving on. So, we are looking at graphs and equations of motion. Now, I know last week you did a little bit of this, and I'm hoping some of you have done this in class. If not, because you're a little bit behind, please don't stress about it. Stick with us. It's always good to have it done in more than one way. It's always good to relook at things. But when we look at graphs of motion, there's a couple of things we need to remember. Okay, first of all, time is always shown along the x-axis, the horizontal axis. That's really, really important. Time is what we call our independent variable. So when it comes to equations and graphs and that sort of thing, time is the thing we actually have the most control over. So something like, I'm hoping you saw this last week anyway, when you look at a ticker timer and you use a ticker timer tape to create your graphs or to look at the equations, the time is the thing you have the most control over. So that's why it becomes your independent variable. Okay, it's the thing you control. On your y-axis, that's your dependent variable. That's the thing you end up measuring. We're going to put displacement, velocity, and acceleration. Okay? Sometimes displacement is referred to as change in position. There's a little bit of a textbooks and stuff are changing what we call that. So whether your teacher's calling it displacement or changing in position, it doesn't really matter. Change in position is just very broad. Okay, displacement is the correct vector term for it. And that, of course, doesn't matter whether it's horizontal, vertical motion, doesn't make a difference. Number two, you must use a suitable axis. Now, that depends, a suitable scale. Now, you need to think very carefully about what the question is giving you. Sometimes you are required to draw an accurate graph. That means you're going to have a whole bunch of points that you're going to need to plot. Then the scale becomes very, very important. If you're looking at a sketch graph, the scale's not so important anymore, but you still need to have values, okay? Then, both axes have 0 as the origin. Grade 10s, particularly for those of you who do life science. I know that in some of your subjects, you're able to do what we call cut the graph. So you cut the axis because you know that your first reading or the first thing you're going to plot on the graph is quite far down the axis, so you don't want to leave this whole big space of empty graph. You don't ever cut your axis in science. Okay, you must start, you must have an origin, 0, 0 from both scales, horizontal and vertical, okay, and then you choose a suitable scale, depending on what you have. They don't have to be the same on both axes, because it depends on what you've measured, how far it's gone, what time sort of scales you're using, but you cannot cut your axis. That's very, very, very important, grade 10s. And then, this one, oh, I beg you, grade 10s, you can never go back in time. In other words, you cannot have a negative time value in any instance. This is really important with graphs because we're going to look at things where we look at the calculation of gradient, and that becomes a problem because in maths it doesn't actually matter which way around you calculate your gradient, and it doesn't matter what you choose as your positive and as your first and your second points, but it does in science because you cannot get a negative value for time. You cannot go back in time as much as we wish we could. Okay, so let's go on to what our graphs will look like. Now, what I'm going to do is this is more a summary of the graphs we can end up drawing and what their shapes are going to be. Grade 10s, your shapes are going to be always the same. Whether it's a graph with lots of different points and pieces and bits and pieces on it, or whether it's just one motion, so it's one thing that's moved, the graphs can only do certain things. Why do your graphs always look the same? Because we only deal with linear motion at school level. Linear motion means we only deal with motion in one plane, and also means that we don't go and decide, for example, that we're going to give you a non-constant acceleration for an entire motion. Okay? If the acceleration changes, we have to start again, and we split up our motion into separate sections with constant acceleration. So we have linear motion, which means we get really nice graphs. Okay? So when we think about what our displacement time graph would look like, we have x, delta x, okay, this would actually need to be called delta x and delta t because we're looking at the change in time and the change in displacement, and that would be in meters, that would be in seconds. Even though we're looking at a sketch graph, we're going to keep the SI units, which is meters and seconds. If you're given a question where they have looked at motion over hours and kilometers, then you can change those kilometers an hour. That doesn't make a difference, but the SI unit is meters and seconds, okay? So if we have constant velocity, that means that we are constantly changing, okay? We're going at the same rate, which means every second we're changing our displacement by the same amount. And the first thing we're going to look at is constant positive velocity. That also means that we're looking at a displacement that goes in our positive direction. And that also tells us that we're going to end up with, and this is really nice, a straight line. Now that straight line, I've drawn it almost from the origin. It doesn't have to be from the origin. Okay, it will have a gradient. It could be from this part of the graph, okay, if we didn't start at the 0 point of displacement. So when we look at our reference, remember we've got a frame of reference. If my frame of reference is here, is where I'm standing, for example, but my motion starts where Katleko is sitting, then my displacement cannot start at 0 because I didn't start at my reference point, okay? Doesn't really matter. The point is it gives us a nice straight line, okay? That's for positive velocity. What happens if we have a negative velocity? A negative velocity means that it's going in the opposite direction, and we can also and what that means is then my graph will change direction, okay? Displacement can be both positive and negative. So if I actually extend my graph over here and I go, well, what happens if I started my 0 point, but I've now decided that going away from me in front of me is positive, but going away from me behind me is negative, and somebody now is traveling behind me, okay, is going away from me towards the board in the negative direction, and that means my displacement is actually getting more and more and more and more in the negative direction, okay? Displacement's a vector, positive and negative direction. So of course you can have a negative graph. What do I need you to get from this? Straight line, constant velocity. What happens if we have constant acceleration? Now, acceleration means that your velocity is changing. So it's a case of you can either have positive acceleration or you can have negative acceleration. Generally speaking, grade 10s, when we talk about negative acceleration, we talk about the fact that it's slowing down, like when a car brakes to stop at a stop street or a robot. What's important here is with acceleration, your velocity is changing. And depending on whether it's getting faster or slower, it depends on how it changes. So if we have a positive acceleration, that means every second it's getting faster and faster and faster. So every second, the object covers a greater distance in a shorter period of time. And your graph becomes a curve. Okay? Your graph becomes a curve. And that curve's the wrong way around. Your graph becomes a curve. Okay. Shorter time period, bigger distance. Okay? Shorter time period, bigger distance. This is positive acceleration. Okay? So this is where it's going to get faster. When it's slowing down, let's consider it as a negative acceleration, then what happens is my graph does not do that. It doesn't do all squiggly thingies. It starts to slow down and curves the other way. So what happens here is less distance, that's my height, over time. Okay, so it's slowing down. It's getting slower and slower and slower. Last thing we can look at is what happens if the car's stationary. This graph will be a straight line again, okay, but it can be in several points because it all depends on where the object is. So we could have a stationary vehicle at a certain distance from my stationary point. It could be actually at 0, so on my axes. It can also be negative. Okay, now if I extend my line, so let's just make my graph go into the negative. Of course it can. It can also be there. But it's a straight horizontal line. That tells me that no matter how much the time goes past here, the displacement from my original position hasn't changed. It is stationary. That also means it's got constant velocity. It's a straight line, which is great. It just happens to have a constant velocity of 0. Okay? So, that brings us to our velocity time graphs. Velocity time graphs are really, really important. They're actually very, very, very useful to us, grade 10s, okay? Velocity time graphs can give us a whole bunch of information, and in fact, they're far more useful to us than displacement time graphs or acceleration time graphs. Because from a velocity time graph, we can find both the displacement and the acceleration of our object. Brilliant. Constant velocity, now this depends on the direction in which the object's moving, can either be positive or it can be negative. Okay? Positive or negative. Constant velocity, no change in velocity over time, which means it stays at the same rate. Positive just means it's going in the positive direction. Negative is going in the negative direction, whatever that might be. And it's a straight line horizontal to the time axis. Okay? No change in acceleration. What happens if we have constant acceleration? Now, this, like we said with displacement, can either be positive acceleration or it's going to be negative acceleration. If it's positive acceleration, we are going to assume that means that it's speeding up, it's getting faster. Constant, we have an acceleration that is the same rate, which means that our velocity is increasing by the same amount every second. It becomes a straight line, okay? And it can start from rest, so that means my original is 0. Might not start from rest, which means it can start from there and goes up. All depends on where we're starting as our 0 or reference point. We can have a negative acceleration, which means it's slowing down, okay, which often will tell us that we start from some velocity and it now gets slower. As time goes down, this can go well beyond the negative point. It all depends on the situation. Generally, we'll go beyond into the negative velocities when we're looking at vertical motion, but we're not going to worry too much about that this year. Doesn't have to go end at 0, does not have to end there. It all depends on what section of motion we are looking at, okay? If it's stationary, well, if it's stationary, there's only one place that this graph can go, and that is on the origin. If it's stationary, velocity is 0, not moving, okay? So that actually makes it quite simple. So I'm hoping what you've also realized here, grade 10s, is that not one of these were curved. Displacement time graph, we could most definitely get a curve off. Velocity time graph, because we only deal with linear motion, so we only deal with constant acceleration, we don't get curves in our velocity time graphs. They must be straight lines. They're either going to be horizontal straight lines or they're going to be at a slope. That leads us to our last type of graph that we can get, which is acceleration time graphs. Okay? Acceleration time graphs are probably the nicest ones we have because actually they can only look into three ways basically. If we have constant velocity, that means the velocity isn't changing. If our velocity isn't changing, there is no acceleration. No acceleration means zero acceleration. My graph goes on the x-axis. Simple, straight line, nothing difficult. Now, this graph, by the way, the constant velocity one over here where a is 0, that could be for an object that is moving at constant velocity or an object that's stationary. Because an object that's stationary has a constant velocity of 0. Okay, doesn't make a difference. If we have a constant acceleration, I've said this to you already, acceleration can either be positive or it can be negative. One of the two. If it's positive, we will only ever draw a straight line because we deal with linear motion. If it's negative, it becomes a straight line. Okay? No curves, no angles, no slopes. Nice straight lines parallel to the time axis. And just quickly, stationary, well, constant velocity, so goes on the y-axis, okay? Goes straight along the x-axis. The shapes are very important. Grade 10s, you're going to get asked to describe motion, okay? Lots for you to take in. We've sort of discussed shapes. I think, Kakleho, we can take a break.
Okay.
When I've got a question. We're going to carry on with graphs when we're done, though.
Okay,
after that.
So you guys hear that there is so much more to this physical science show, grade 10s. Come back with all your focus, all your attention, because you really do need this. See you just now. Welcome back, Mindsetters. As you know, we are doing physical science for grade 10s, guys. We are doing graphs and equations of motion, aren't we, Tracy?
We are.
And we
I'm
are. And
loving
it's
it.
been awesome so far. We've learned about the different kind of graphs. So I know that if you're sitting in front of your screen, your notes are already looking so nice. Remember to use color, make it exciting for yourself, because it is very important, grade 10s, as you know.
I know, it's very important. I love it. Like I see
Yeah.
with my kids at school as well. It's like, oh, nice and colorful.
Yeah.
Thanks why I like the board so much, because it's
Because you can put color.
I know. It's quite scary, actually. Anyway, so back to graphs. Now, before the break, we were really just looking at the shapes. Now we need to talk about what can we learn from the graphs, why are they important. So now we get into remembering some maths, which of course we know is always fun. And I just realized I put the same thing. You know what? It's my fault. I was obviously asleep when I wrote this. So what we're going to do is I need to just quickly change something and go, that's not slope. Let's change that to area. Because slope and gradient, I'm hoping somebody at home was actually going, you know, Tracy, you need to get your head checked because slope and gradient are the same thing. Anyway, so let's pretend it said area. Okay, it's been a long week already and it's only Tuesday. When we look at our graphs, we have our three graphs: displacement time graph, velocity time graph, acceleration time graph. What can we learn from the graphs? Because that's important. It's not just enough to be able to maybe draw them or to be able to describe the motion that's happening, but we want to be able to get information off the graphs. So when it comes to a displacement time graph, the area doesn't actually help us. The area under the graph doesn't help us because the area under the graph becomes displacement times time. That really means nothing. But the gradient of a displacement time graph gives us velocity. So if we take the gradient of our displacement time graph, that gives us the velocity, and it's an average. When we get to the velocity time graph, now, like I said to you earlier, this is such a useful graph for us because if I'm looking at area, and area becomes half base times height, which means it's v times t, velocity times time, that is actually displacement. So if I work out the area under my velocity time graph, I can work out the displacement of my object, whatever it might be. However, if I take the gradient of my velocity time graph, that gradient becomes velocity divided by time, acceleration. So that's useful. We can do something with that. We go now to our acceleration versus time graph. The area under the acceleration time graph, which then becomes acceleration times time, is velocity, okay? But the gradient of a velocity time graph, not that useful. So we don't do anything with it, so it doesn't help us, okay? This summary, grade 10, so important. So important. We can do all sorts of weird and wonderful things off it, okay? Now, I hope you're ready to tackle a problem. We only have one. It's not very difficult, but it's one to help you get into the swing of things, and let's see what we can do with it, okay? Says to us, Tandy takes 200 seconds, okay? So that's just over 3 minutes to walk 100 meters to the bus stop every morning, which is quite nice, which means that's actually quite a nice brisk walk. In the evenings, Tandy takes 200 seconds to walk 100 meters from the bus stop to her home. So if we want to look at it, and we'll just do this at a really, so here's Tandy walks from her house to the bus stop, and from the bus stop to her house. That's what she does, okay? Two things. We need to make some assumptions here. One, that she's walking at constant velocity, because they didn't say anything about her acceleration. They didn't say it takes her 10 seconds to walk the first meter, then it takes her 20 seconds to walk the next 50 meters, and then she takes a minute to walk the next 10 meters. We're just assuming constant velocity, and it's the same in both directions, okay? They say to you, draw a graph of Tandy's position as a function of time for the morning. In other words, position versus time, displacement time graph. We are going to use her home as her reference point. Okay. Reference point. This is a sketch graph. Grade 10s. Okay. Sketch graph. We need an axis. So we have a displacement, and there we go. Let's just quickly get rid of that extra little thing. We don't need it. And let's just move this. There we go. Okay. Displacement time graph. That means labels, displacement. They told you that she goes 100 meters. Meters is a good unit. And time in seconds. Now we know that she goes, it's the sketch graph, so she goes 100 meters, so let's put the 100 in here, and it takes her 200 seconds, and there's our 0. That's enough information. I don't need anything else with regards to what we're doing, and I said assume constant velocity, which means it's going to be a straight line, and there we go. So let's go straight line. There's my graph. Straight line graph. Okay? You're with me? I hope so. Let's see what it says to us now. Draw the graph of velocity versus time. Okay. Second graph they want is velocity versus time. And now we look at the information we've got here, grade 10s. I know the displacement and I know the time, but I actually don't have the velocity. But if we go and remember what I just said to you from a displacement time graph, I can work out the velocity by looking at the gradient. So in order to draw this velocity time graph, I need what was her constant velocity. So we go, okay, before I draw the graph, let's work it out. So the velocity is equal to the gradient of the graph, okay, velocity is equal to gradient, that means it's going to be equal to the change in displacement over change in time. Now, if you need to remember, which is rise over run, x1 minus x2 minus x1, t2 minus t1, write it in. You don't have to, but I'm just going to remind you from a math point of view, so we're all on the same page. Point 1, and this would be 2. Okay, 2 minus 1. The 200 seconds has to be our second point, because I said you right at the beginning of the show, time cannot be negative. So we went 100 minus 0, 200. Ooh, wow, my 2's having a bit of a moment. So 100 minus 0, 200 minus 0 gives me 100 over 200, 0.5 meters per second, constant velocity. Now, I have enough information to draw my graph. We need an axis. We know it's positive. And there we go. And we've already decided, we know that it's a straight line. Constant velocity, it's going to be a straight line. Let's just add in all the values, well, all the information. Let me just put that over a little bit, because that's going to be 200. This is my change in time, so that's in seconds. There's 0, that's 0.5, and this is velocity in meters per second, straight line. Nice and easy. Next one was draw the graph of acceleration versus time. I'm hoping you guys are screaming at me going, oh, come on, Tracy. That's just like a doddle. That's a walk in the park. Of course it is. Because constant velocity means what about the acceleration? It's 0. Okay. You could work out your gradient if you wanted to, if you weren't sure. But then you're going to have 0.5 minus 0.5. You're going to have a 0 divided by 200. It's 0. All right. But I'm hoping you remember constant velocity means 0 acceleration. So this graph, okay, there's our lines. Let's just get rid of my extra one, because I can draw extra ones. And this is going to be 0 acceleration. So we're going to put it, make sure it sits on the y-axis, on the x-axis, sorry. There we go. Let's add in the values we know. Well, that was at 200. This is delta t in seconds. This is A. Ooh, and I've lost my pen somehow. That's A in meters per second squared. And that's 0. Nice and simple, okay? We could add to this question and now say, well, what happens when Tundi returns home? All of this we just reversing it. Still 0 acceleration. Her velocity actually is now negative because she's going to be coming towards us, so it becomes a negative value, but it's exactly the same because she does the same distance in the same time. She's just changed direction. Okay, so with graphs, because now we need to move on to equations. Yay, I'm sure you're all very excited. Graphs, you must know the shape, okay, and you must know how you can calculate stuff off them. Very, very important. From graphs. And I'm hoping some of your teachers have actually done this with you, and you could have done it with ticker timers. Fortunately, we are a little strapped for time, otherwise I'd love to do it with you. But from the graphs of motion, you can actually get our 4 equations of motion. Equations are so important. They tell us so much. Okay, so here, now there's 3. I'm going to put the 4th one up in a second. We have 3 really important equations of motion. These 3 you're going to use all the time. Yes, grade 10s, they will be on your information sheet. But do yourselves a favor, learn them, okay? You do not want to be spending half your tests and exams looking for an equation. You need to know them. It's really, really important, because if you know them, then you know how to use them. And they are an incredibly powerful tool. Okay, first equation, VF equals VI plus A delta T. What do all these things mean? Well, VF stands for final velocity. and it's measured in meters per second. Final velocity in the motion. VI, I'm hoping you'll go, well, that makes sense. If F means final, then I must mean initial. So VI stands for initial velocity, which will also be measured in meters per second. A, oh, we can do this. A means acceleration, which is measured in meters per second squared. Okay. And delta T would mean change in time. Of course it is. And unfortunately, you have to write the delta. I'm sorry, grade 10s. Gets a little complicated. Okay, which is in seconds. Grade 10s, please be careful. This section of work has actually been in the curriculum for many, many years. And a lot of the old textbooks, depending if they're pre-2008, will be using S and just T and V and U. Their symbols are slightly different. If you have any friends that are working in the IB curriculum, they also use slightly different symbols. It's still the same equation. The principles are still the same, but make sure you use the correct ones when you write these tests, okay? It's really, really important. Now, that's the first one, which tells me final velocity equals initial velocity plus acceleration times time. Nice and simple. Next one, and I forgot how to square over there, is delta x equals vi delta t plus a half a delta t squared. So in other words, my displacement, that's what delta x stands for. Okay, that's displacement, which means it's displacement, so it's measured in meters. If some of you are looking a little bit further ahead, or you are in 11 or 12 doing a bit of revision, the delta x sometimes is replaced with delta y. Delta x is horizontal motion, delta y is vertical. Okay, still displacement. Delta x equals vi delta t, so my displacement equals my initial velocity times time, plus a half times my acceleration times time squared. Okay, this is not a fun equation to use, but hey, there we go. These 5 are my unknowns, so it's the only 5 concept ones you're going to be working with, nothing else to add into motion. My third equation says to me that if I take the final velocity and square it, it's going to be equal to the initial velocity plus 2 times my acceleration times delta x times the displacement. Now, there's a fourth equation that I have not put on the board. Personally, and this is a personal thing, grade 10s, I don't like you using it because sometimes you use it in the wrong place and then things get all messed up, but it will be given to you. And it says to me that delta x is VF plus VI divided by 2 times by time. What's nice about this equation is you do not need acceleration. It's unusual, but in reality, grade 10s, you can answer every single equations of motion question with the first 3. Okay, my grade 10s hate me because I don't teach them that equation. Doesn't matter. It's one that you can use. Okay, it's a personal choice. So, Kakleho, now that I've completely overloaded them with information, I think we can take a short break, and then I've actually got some really nice questions to do with equations when we're done.
Okay, awesome. So let's go for a really quick break because we do really want to get back to those lovely questions that Tracy has prepared. But if you have questions of your own, this may be the right time to send them through. See you right after the break. Welcome back, Mindsetters. I hope you guys had a refreshing break because there is still more to go through. On the page, lovely stuff, guys. I love seeing so much interaction, so many questions, so much interest. I know you guys are helping each other and actually care. It's nice that you care because then you stand a shot at passing really well. Do you want some questions?
Hit me with it. Let's see what we can do.
So we have a question from Nsako, Pleasure Nsako. She asks, I think this is what you're asking. You can send a message to correct us, but she asks, what is the difference between the distance versus time graph and the displacement versus time graph?
That's actually a great question because I didn't really cover it. Remember, distance is a scalar, sweetie. So distance doesn't have direction. So with all of my displacement graphs, if we go right back to the beginning where we looked at the displacement over here, okay, I could draw displacement as a negative value. You would not get that in a distance graph because distance doesn't matter about direction. So the shape of the graph would look the same, but it would never go below the y-axis. Okay, never go below the x-axis, sorry. So it would never be negative. That's the only difference. The shapes look the same, but it just never goes to the negative, basically. Yeah, good question.
Okay, and then there's another one by Mfundo. He asks, is acceleration under a vector or a scalar?
Mfundo, acceleration is a vector. Okay, acceleration can be positive and negative, so it has direction, absolutely. And next year in grade 11, you're going to do a whole thing on Newton's second law. It's a really nice section where we start to do the whole direction of your acceleration in a lot more detail, but it is a vector. Okay, it can be positive or negative depending on the direction, and it's a little harder to see than some of the others because when we talk about a negative acceleration, it doesn't mean that the object's necessarily moving backwards. It just means that the acceleration acts in a different direction to the direction of motion. Okay, so it's definitely a vector.
Okay, and then we have another one by Nsako. What is the difference between velocity and displacement?
Okay. Displacement is the straight line distance in a certain direction from the beginning point to the end point of a motion. So it's a distance, it's in meters. Velocity is how fast you take to do that. Okay, so velocity is like speed, but with direction. So velocity is how fast we get it. So velocity can be 2 meters per second, which tells us that I cover 2 meters every second. Okay, so velocity is a speed with direction. Displacement is a distance. It's a length. Okay.
Okay.
Cool. All right. So we have some problems with equations of motion, and I'm going to show you some ways on how to deal with these problems, grade 10s. They're actually not as difficult as they look. A lot of the times, it's not that you can't do the signs. You're just not sure what the question is asking you. So, hint, take out a pen. You start to write things down. It says to us, a train starts from rest. This is important. If something is at rest or comes to rest, it means it is stationary. So if my train starts from rest, my initial velocity is 0. Okay? And accelerates at 1 meters per second squared. Before I go any further, what we're going to do is we're going to write a list. There were 5 unknowns. We go back here, okay, to the equations. I have a list, VF, VI, A, delta T, X, okay? I always write that down. Watch what I'm going to do. So VI, VF, A, delta T, delta X. I may or may not fill these bits of information in, okay? But this helps me decide what I need to do. So they say to me it accelerates at 1 meter per second squared for 10 seconds. Ooh, 10 seconds, not, that was seconds, not displacement, okay. And then they say to me, question is how far displacement. That's what I want. Now we go, okay, I want displacement. What should I use? Which equation? So let's go back to our equations and we go, okay, I don't know final velocity. I know initial. I know acceleration. And I know time. That equation doesn't help me because it doesn't have displacement in it. So that's useless for us, okay? I want displacement. I know initial. I know time. I know acceleration. Brilliant. That's the equation I need to use. It's exactly what you do, grade 10s. You go through it step by step. So we go, okay, I want to use delta x equals vi delta t plus a half a delta t squared. I wrote my list so it becomes easy. That's 0. It does it for 10 seconds. It's a half. It's 1 meter per second squared. And it's for 10 seconds. Now it's a math problem. Grade 10s, if you show me all the steps, brilliant. If you don't, it really doesn't matter, but I'll show you. 0 times 10 is 0. A half times 1 is a half times 10 squared. 10 squared is 100. So that makes it a half times 100 is 50. 50 meters. Okay? So that means the train moves 50 meters in 10 seconds. Okay? You guys ready to tackle another one? I hope so. So here we go. A bus is going at 30. What did I say? We need to have a list. So VI, VF, A, delta T, delta X. So it is going at 30. It comes to a stop and stops. Stop means that it's going to come to a rest, not moving. Final velocity is 0. And it does this in 5 seconds. What is its stopping distance for this speed? Delta X. Like I said to you earlier, there's lots of ways you can do this. We can work out the acceleration. It's not that difficult. And then use that to work out delta X. You want to make it as simple as possible. Remember, you have an equation that says to us that delta X is equal to VF plus VI divided by 2 times time. So VF, we've said, is 0. Initial is 30. You need to divide that by 2 and then times it by 5. So 30 plus 0 is 30. 30 divided by 2 is 15. So I have 15 times by 5. 75 meters. Okay? I think we can go to something a little more challenging. All right. A motorcycle has a uniform acceleration. Uniform, grade 10s, same as constant. Okay? Uniform, same as constant, doesn't change. And it has a uniform acceleration of 4. Assume the motorcycle has an initial velocity of 20. Calculate the velocity and displacement, at the end of 12 seconds. So we actually have 2 things to do here. VI, they said to us, was 20. VF, we don't know, but it's one of the things I need to calculate. A is 4. Delta T is 12. And delta X is what we are looking for. Didn't say which order you had to do this in, so it doesn't actually matter, but let's start with VF. You go back to your equations, and we don't want to use an equation with delta X in it. I don't know delta X, so I can't use displacement, but I do have an equation which says to us that VF equals VI plus A delta T, where VI, they said to us, was 20. A is 4. T is 12. 4 times 12 is 48. So we're going to have 20 plus 48, which gives me 68 meters per second. You pretty much could only use that equation at this point because we don't know X. Now they say to calculate delta X. And we go, okay, well, I want to show you that it doesn't really matter how we get around there. We want, so I know this is 68. ooh, that looks more like 68. When I actually do this, grade 10s, I write this in and actually underline it so that I remember it's something I found. If I can avoid using it, I will, because in case I've made a mistake and then I'd carry it down and things get all hairy. So let's work out delta x without using VF. Okay, we have two equations with delta x in. We have VF squared equals VI squared plus 2a delta x. Okay, it's got VF in it, and I worked it out, so that's not a good idea. We have another one that says to us that delta x equals VI delta t plus a half a delta t squared. So we go, okay, VI, we realized was 20. T is 12. A was 4. And T is 12 squared. I do suggest you work these out separately because you want to make sure you get it right and you want to make sure you don't make a mistake on your calculator. 20 times 12 is 240. I've already worked these out. And a half times 4 times 12 squared is 96 because, no, ooh, no, that's wrong. I just realized. Oh dear. That's because that's not 96. Oh dear.
Oh, you have to get your eraser from the top.
No, I don't need the eraser.
Oh,
I
you
need
don't
the calculator.
Oh, okay, cool.
No,
I think
we'll
it's
find
my
it.
computer.
Yeah, thank you. This is why I have you. Oh, there it is.
And then I think you choose the black one, eh?
Yeah, I think we're going to... Sorry, guys. This is what happens when you...
That's okay. So you guys can get your calculators out. Maybe you can actually do it before Tracy even gets around to doing it. So send us through the answer. If you have quickly typed it on your calculator, you already know your equations. You already know how everything works, basically. So
Yep.
tell me quick, guys. Help us out here. Let us know.
I think I was too quick for them, though.
Okay.
Okay, but let's just erase the
We have
96.
some really fast mindsetters, by the way.
No, we
Tracy.
do. I agree. Okay. What I actually did, mindsetters, is when I worked this out, I went and put 4 as my time and went 4 squared. So I got 96. There's not a chance that 2 times 144 is 96. So we've got a half times 4 times 12 squared gives me 288. Much better value. That actually just looks better too. You see, grade 10s, this is why you need to do it step by step because even I make mistakes, okay? I was in a bit of a rush, so this is my own fault. This is actually complete. I'm sorry, I am
Don't
human.
worry, we'll forgive you. You're human.
Thank you. But at least I picked it up. Could you
Yeah,
imagine?
yeah.
But that's why you do it step by step. And it's also good for me as a teacher when I see someone do it like this, it's so easy for me to be able to correct those mistakes. Where if you go from here to the answer and you've put it all in wrong on your calculator, then I can't help you, okay? So now we've got 240. I'm not going to try and do this in my head because I'll probably get it wrong. 240 plus 288, and it's 528. No, 588. No, 528. So I can't even read today. Oh, boy. Okay. 528 meters. I want to show you something. As I said to you, it doesn't matter how you get here. Okay? This was one way. This is the way I would prefer you guys to get this answer, simply because I didn't need to use that 68. But what happens if you do decide to use the 68? Then you're going to use this equation. VF squared equals VI squared plus 2a delta x. Now, I'm going to be honest here, grade 10s, I'm lazy when it comes to this. I don't like this equation because I'm going to have to manipulate for x. Now, I'm going to have to do this really quickly. So that's 68 squared. This is 20. 2 times, and my acceleration was 4. Okay, it's still delta x. Sorry, delta x. So 68 squared is 4,624. 4,624. 20 squared is 400. This, sorry, not yet. Let's do this. 400 plus 8 delta x. I'm sorry, we're running out of time. So I'm going to give 4,624 minus 400 gives me 4,224 equals 8 delta x. Now watch. 4,224 divided by 8. Oh, look at that, 528 meters. Okay, so it doesn't matter. 528 meters. So it really doesn't matter which way around you do it. Why don't I want to do this? Because I might have made a mistake with F. Okay, with VF. And I think I'm done.
Yes, thank you,
I think it's time for
Tracy.
coffee.
I think
Oh
it
my
may
goodness.
be time for a little bit of a nap for you.
I think so. It's been a long day.
I know,
Thank
I
you,
can
grade
imagine.
10s.
Thank you, Tracy. That
you're
was awesome. Thank you, grade 10s. I know that you guys enjoyed it because I can see what you've written on the page. So, thank you for that. And thank you for joining us. Thank you again to Liberty, guys, for bringing us such an awesome show. Grade 11s are up next. Bye-bye, grade 10. See you next time.